Let's look at the guanylate kinase enzyme in all atom simulations. We looked earlier at this system in coarse-grained in an elastic network model, and here we now have the equivalent setup in an all-atom MD simulation. So let me already put a high force, then we can achieve something. And if you remember, in the elastic network, I sort of open-closed the thing because it has a kind of a U shape. Let's see whether you can see that, sort of like this, and it would open-close like that. And we can try and look at this. Let's just look at the cartoon. And maybe to make it nice, we give it an outline. And change the colors. And now I could try here, the open and closing. And you can already see the modifications I do, they remain very local. They will rather unstructure the actual loop I'm pulling on than have the full bit of the molecule come with. So if I wanted to get a similar opening as previously, I really need to individually pull on all the things. And unfortunately, to see the allosteric transmission, it will also be very difficult compared to elastic network, which is the advantage. You can see in the elastic network, we pulled somewhere in the middle here, and it made the tips move. This is not happening in this all-atom model. I will probably crash actually the simulation soon. So you can see it's difficult, much more difficult to probe such long-range modifications, slow conformational changes in an MD simulation. You would probably need to use some collective variables for that, and we're actually working on that on interactive simulations driven by collective variables. And that's as much as I wanted to show you for this system. We can actually show the hyperbols as well. And you can see, I can of course also manipulate those, but it's rather perturbing the structure than achieving the actual deformation I wanted to see of the opening closing. Thank you. Ctrl X to quit. Back to the menu.